So there we go. Okay, so let's see. So I see two problems on the final about Lie brackets. One of them is about showing that the restrictions of smooth vector fields to an embedded submanifold, that its Lie bracket is also tangent to the restricted submanifold. And then there's also a question where we're just computing a Lie bracket. Does one of these sound more appealing?
I think the restriction one. There's also a problem, I guess it didn't make it to the final, I can't remember now, that has like several parts as well. So I guess either of those two.
Okay. Well, we can look at the other problem. Is this the one that's just like, we're gonna do something called bootstrapping? We're gonna like bootstrap a solution to them or something?
That's
okay.
That was yeah.
Okay.
Also, actually, because I think this is like relatively quick, and relates to part B, I would assume. Problem 4 on the final, show that every continuous map SP to Sn is null homotopic if P is strictly less than N. Apparently, you're not allowed to just say, well, the homotopy group of the P's homotopy group of Sn when N is bigger than P is 0. Which is what I just said. And he's like, yeah, that begs the question completely. So I have no idea how you're supposed to show it.
Yeah, that just, yeah. Yeah, I suppose that's saying that the homology groups aren't the same. Is that weaker than saying that every map is null homotopic? Right, because saying that because like if all homology groups are the same if and only if the two spaces are homotopic, but being null homotopic means that you're homotopic to a constant map, which is a stronger statement than just saying that there does not exist a homology equivalence. So maybe that's one of the, yeah, okay, yeah, maybe we should start with that as like a warm up, which, you know, gets us from part B stuff to part C stuff. And then we can talk about one of these Lie bracket things. Okay. So okay, so the way that I've done this problem in the past, let me clear my OneNote note before I share it.
Like my only guess is maybe he wrote that question thinking you'd read it as prove that the Pth homotopy group of Sn is 0 when n is bigger than P. And you do that by that sort of Meyer-Vittorius or something. But like, I was annoyed at him because I'm like, if you write it like that, it's not clear that I can't just say, yeah, this is a fact that I know.
Right. Yeah. Well, for this, he wants you to use some differential topology. And essentially, what you do is you cite the Whitney approximation theorem, and then you cite Sard's theorem, and then you can construct an explicit contraction. Because what's really going on here is that you just have to show that that continuous maps from SP to Sn are, I don't want to say like essentially, but are, what's the word that I'm looking for? Like,
oh, is it where you say,
they
oh, well,
should be
it's
not
homotopic.
surjective.
Yeah, okay, so that's
right?
the avenue.
Yeah, and then because it's not surjective, you can remove a point from the image, and then that's just, so like I said, Fred loves problems where you can just turn the problems into Euclidean space. So you can remove a point and turn it into Euclidean space and then build an explicit contraction, right? And so that's the
Okay, so that's the thing that you're supposed to do to make this a differential topology question.
Yeah.
Okay, then I kind of know what we're doing then. It was just that like I had no idea what technique he wanted us to use.
Yeah. So so this is a problem on the number 4 in the final. So number 4 for the 2021 part C final. Yeah, I'm trying to do a good job about like citing which problems I'm doing on different things, but okay, right. So for this, so there's a couple of steps, and I guess that I'll just do like an outline of a proof instead of proof. So step 1, you use the Whitney approximation theorem. And the Whitney approximation theorem states that every, or I guess because it's an outline, I don't have to state everything. The Whitney approximation theorem states that every continuous map between two smooth manifolds is homotopic to a smooth map between the smooth manifolds, right? Between the same manifolds. So since we're looking for homotopic equivalence anyway, I can replace the original continuous map with a smooth map, right? So you replace the continuous map with a smooth map, and they're in the same homotopy class. Okay. So that's good. Okay. And hey, now we could do differential topology because we have a smooth map instead of a continuous map. Okay. Step 2 is to use Sard's theorem. To show that the smooth map is not surjective. Right. So Sard's theorem states that if the dimension of the domain is strictly less than the dimension of the codomain, then the image of the map has measure 0 in the codomain, right? That if you put the normal measure, like the normal Borel measure on this codomain manifold, which you can because it's locally Euclidean, so you can just like put the normal measure on it with like the normal open balls that you generate. If you haven't taken measure theory, don't worry about it, right? The thing that you should know about measure 0 is that the picture to keep mentally to keep in mind of measure 0 is that like the rational numbers have measure 0 in the reals, right? And in particular, there's tons and tons of points which aren't in the image, right? Measure 0 is small compared to the codomain, and that means that the map is not surjective. So in order to show that it's not surjective, we really only need one point which is not in the image. And we're really hitting this with a gigantic hammer, right? By saying that the image has measure 0. All that we need is one point, but like, you know, we have a tiny nail and a gigantic hammer, so we might as well use the gigantic hammer. Okay. Note that in order to use Sard's theorem, we need to use a smooth map because you can't have something like a space filling curve, right? If it's just a continuous map, right? A space filling curve is continuous, but its image is the entire space. So we really do need to restrict to smooth maps for this step. Then step 3, you view the codomain as Sn set minus a point where P is not in the image of your map, and use fact that Sn set minus P is diffeomorphic to Rn. And then finally, for the last step, you just construct the required contraction, or I guess the required homotopy using the contraction Rn homotopic to a point. And so there are some details there, and it's kind of fun practicing constructing, making these homotopy equivalences, right? Just like writing them out, like learning how to like compose the homotopies correctly and things like this. Yeah, but this is essentially what's going on, right? Is these 4 steps. So like the first 2 steps are like big theorems, and the second 2 steps are like standard argument. Questions, comments, or concerns?
Sorry, like when you say to construct the required homotopy, like you're not saying like write down something explicitly, are you? Like an explicit function?
You certainly can write down an explicit function here. Because it's a straight line homotopy. Yeah, so the homotopy that so for example, H is a map from Rn cross 0, 1 to Rn. Here I have I'll call this a vector V, and here I have an element T, and so you can just send this to T times V. Then H of V comma 0 is always the origin, and H of V comma 1 is just the identity function on V, right? So this is going to be a homology between the identity function and a constant map, which shows that this is contractible. And then you compose this correctly with the diffeomorphism that you construct in step 3, and the function that you got from step 1, the smooth function, and then you can actually construct an explicit homotopy between a constant map and that original function f. Okay. Parentheses around this. Okay. Any other questions? Okay, cool. All right, then let's move on to question 5. So number 5, also from the final exam. I'll just write final exam now because it's the same final. So what even does it say specifically? Okay, so let N be an embedded submanifold of M. Let X and Y be two smooth vector fields on M. Show that if the restriction of X and Y to N are tangent to N, then their Lie bracket is also tangent to N. Yeah, so I guess that the first thing that you should think of for this is that this should be true, just heuristically, because the Lie bracket on the Lie bracket of two vector fields on a manifold just gives you another vector field on the manifold, right? So what this is really saying is that, right, what we're really asking here is that the Lie bracket of the restrictions is equal to the restriction of the Lie bracket, right? That it doesn't matter whether you restrict first and then take the Lie bracket, or if you take the Lie bracket and then restrict, right? So the solution that I'm going to present for this one actually isn't mine. It's one of Jonathan's from when I took the topology qualifying exam prep seminar from him, but that's because, you know, this was all right. Fred reuses problems, and this was also a problem on our final exam prep document from 2019, and it shows up right. So, okay, so since I have that N is an embedded submanifold of M, let's give it an embedding. So let's let phi from N to M be a smooth embedding. In particular, it's an immersion. Right. Who here remembers what it means for a map to be an immersion?
The differential is injective everywhere.
Yeah, that's right. The differential is injective. So that is the differential, which I'm gonna denote this way, at P from TPN to TPM is injective for all. And so Fred makes this joke that says that differential topology is the field which is invariant under change of notation. Okay, so this is the same as this, okay, which is the same as like this, right, which is all just differential of phi, right? Right, different people use different notations. Okay, so by assumption, for every point in my embedded submanifold, x sub phi of p and y sub phi of p are elements of the image of the tangent space of n under this map, which of course is contained in T of Vp of m, but that's secondary. I guess in order to make this look more right and proper, I should just formally write it like this. I just continue the line instead of adding it to the top. Okay, so then because this map is injective, I can just take the pre-images of these vector fields. So I'm just going to define vector fields x tilde, y tilde on n by x tilde at p is equal to the pre-image under this map of the correct vector field, and similarly, this is the pre-image at P of its corresponding vector field. Okay. So what is it that we've done? A bunch of formalism. Okay, not a joke. Okay, so we have, very concretely written what it means for a vector field on M to restrict to a vector field on N, right? So what are we saying, right? X and Y are vector fields on M. And if I look only at the points where the vector field is defined on N, right? That's what phi of P is, right? Phi of P are all of the points that we identify with N, right? Then those should be tangent to N, and therefore I can pull back those vector fields to get vector fields on N, right? So now I'm viewing N and M as two different spaces. Instead of thinking of N as being inside of M, I'm thinking of N as being separate from M, which was definitely very easy to understand. Okay. Okay. We want to show that X, Y, P is in, yes, cat. Okay. I don't know if you can hear my cat, but she's very cute. For all P and N. Yeah, so this is exactly what it means for the restriction of this of the Lie bracket to be tangent to N. Right? If the Lie bracket at every point that we identify in N, right, is in the image of, right? Hello. Yes. Okay. Sorry, my cat is really breaking my train of thought here. Yeah. So this Lie bracket, right? This is a vector field, and I want it to be in the same space that both X and Y were, right? So this was the condition on my original vector fields up here, and I just want to show that the Lie bracket has the same condition. Right. Okay. So to do this, we check for some smooth C infinity M function, right? I want to show that it does the
Jacob,
same thing.
Can
Yeah.
you just clarify real quick for me what the notation phi star of TP of n is?
Yeah, so phi star is the differential. So that means that phi star, right, I have to change colors like this because it's being dumb. Yeah, so this is the map when I restrict it to P. Right? So phi star is a map from the total space to the total space, right? Such that it restricts for every P to the, I guess that this should be 5P instead of TP. So that was a typo. I'll highlight the typo. It won't let me change to the highlighter. So this was a typo. Yeah, so it's the differential. So I'm going to take the image of this entire space. I suppose that I could take the image of this entire space with respect to P, and that would also be fine. Yeah, but this basically is shorthand, and I should say that this is shorthand, right? This is shorthand for saying x, y at phi p is tangent to n when viewed as a subspace of M, right? That's what this entire condition here is saying, right? When you break apart what like the differential is doing, what the image of the tangent space of N is doing, and the image of that under the differential, that's what this is saying. That like, obviously, it's tangent to N in N, but now I'm asking if it's tangent to N, would I take the image of that tangent space under an immersion? So because the differential is injective, right, this tangent space fits nicely inside of M, and so this makes sense. Okay, perhaps that was a little bit of over explanation. Okay, so then I evaluate this Lie bracket on F. So that's going to be, right, just using the definition. Okay, so let's break apart what each of these mean. Right, so let's just focus on this piece first. Okay, so what does this mean? Well, okay, what is X evaluated at this point here? Well, I just went through this work to define this new vector field X tilde, so I'm going to use that X tilde. So this is going to be phi star of X tilde P of dyf. So I haven't changed the dyf. I've just used this definition up here. Hopefully you can see my mouse. I think you can when I share my screen, right? So I've just applied the differential at either side to this. Okay. This is going to be equal to X tilde P of dyf composed with phi. Okay, so what's going on here, let's just make sure that we understand every step of like what these things are doing and like why these things make sense to go in this order, right? Because that's probably the part which is most confusing. It's just like, wait a minute, what are all of these things? And what are these things doing? Another way that this is written, and honestly, this is the way that I prefer writing this, is instead of writing this capital D of Y, I just prefer writing the vector field right next to the function, right? So another way that you could have written this equivalently, like this first step, you could have written this like phi star x tilde p of just yf, right? And this is like how Lee likes to write it in Lee's textbook. He just likes to write these like adjacent, right? But okay, so what's happening here? So, right, what does a vector field do to a function? Right, just as a general statement. And I drew this yesterday in office hours, but I think that's worth drawing again. So if I have a vector field X, so this is a vector field, I can give the vector field two different pieces of information. Right? The first thing that I can give a vector field is I can give the vector field a point in my manifold. And X is a vector field on the manifold M, so this is fine. Right? And I get X sub P, and this is a derivation. Or you could call this like a tangent vector. Because what does a vector field do? A vector field at every point picks out a tangent vector, right? And then once I have my derivation on my tangent vector, and maybe I should move this over slightly and rewrite so that this is easy to read for people who look at these notes later. So this is a derivation, or you could think of this as a tangent vector. Well, I can give a tangent vector a function, right? A C infinity function on M, and I get this thing, and this is a number. Okay. And what this is doing, right? I say that this is number, but really what this is generalizing is that this is the directional derivative of F in the direction of X sub P, right? That's what it's generalizing. If I give you a tangent vector and a function, then you can ask what's the rate of change of the function in the direction of that vector. And that's how we combine a function and a tangent vector, right? But you can go the other way, and you get this thing called xf, where first you give it a C infinity function, and then you give it a point P, right? And it doesn't matter which way you go in this like order, you get the same thing on the bottom from the top, right? And so what we're looking at in this is this guy, right? What is it, right? Well, once you have a function and a vector field, right, that defines another function. This thing here, this is a C infinity M function, right? You give it a point and it gives you a number, right? Which tells you what's the rate of change of that function with respect to this vector field, right, at that point. Okay, so when you look at like what these steps are, right, phi star is the map which takes this entire bit here, right, which is, okay, so to explain this equation, right, I think that this equation is an easy one to understand because I'm just reassociating this composition. So the real one to understand is what's going on here. Well, okay, So y of f, like I said, this is a C. So f was a C infinity function. Then y of f is a C infinity function. Then I apply a vector field to a C infinity function and I get a C infinity function, right? So this is just, right here on the left side, this is just the differential of some C infinity function, right? And so the way that I take the differential of a C infinity function is I just pre-compose with that C infinity function, right? I get a C infinity function and I pre-compose it with the original, right? This is actually the definition. This is what it means to apply the differential, right, of the map, right? You just pre-compose with the original function. Okay. And so that's how you get from the left side to the right side. Okay, so I guess that was supposed to be green, but my colors are all wrong. Okay, so going back to my original black statement, so I have that xvp of dyf minus yvp of dxf. If I do this thing that I did in blue to both statements, okay, I get that this is xp tilde of dy tilde f composed phi minus x y p tilde of d x tilde f composed phi. So I just did the same steps to both components, right? It's the exact same argument that I did in blue for the other term here. But then this is exactly the Lie bracket of x tilde y tilde evaluated at p of the function f composed of phi. And then using that thing, which I spent a long time explaining probably poorly, the way to turn this into a differential, right, is to just move that differential to the front. And then I get the differential of this applied to x tilde comma y tilde of p evaluated on the function f. And surprisingly, this is exactly what it was that we wanted to show, right? I wanted to show that this was in the image of this map. And hey, I just wrote it. Thus, the original Lie bracket that I was looking at is in the image of phi star, right? Specifically, it's the image of this vector field, or this tangent vector, because I evaluated it in P. Okay. Questions, comments, or concerns, of which there are probably many.
Okay, just to make sure, so your phi star is still evaluated at p, right? It's not the global differential.
Yeah, it certainly looks that way because I'm evaluating at p here. So yeah, I can add in a p. That seems fine. Although, I don't know. On my notation, I'm not evaluating this function at p, right? I'm just taking the different, I'm taking a vector field of a function, but this one's evaluated. Yeah, so there's some sloppiness here, probably. And then this could probably also be evaluated at p. And then that would probably make all of this much nicer. But I'm hesitant to add that in. And so if anybody's interested in looking at maybe a better write-up, although it's the same write-up because I use the same work. This was problem set number 3 from the topology Qual prep seminar 2019 website. And so Jonathan also wrote some notes there. But they are very similar to what I wrote here. But who knows? Maybe he wrote something slightly different that I missed that makes you go, oh, and then right clicks. Okay, someone also messaged me and asked if we could talk about question 6. Okay. We can certainly try. I think this is something that I've done before. But now, okay. Unless there are any other questions, comments, or concerns about question 5 before we move on. Which is totally fair. Okay, so yeah, so I'll sketch an idea maybe. So let's just draw 2 half space. Right, 2 half space is great. So 2 half space is saying that the second coordinate is positive, right? So 2 half space is this stuff up here. And in the problem, we have an embedding. So that way this white, or the yellow set, gets embedded into some subset maybe. And so I won't draw like all the way to the right or all the way up like I did before, right? Maybe it's somehow restricted. And so we want to show that the only places that you can send boundary components to are other boundary components. And really, this is just going to come from the fact that we have an open embedding. So idea is to let P be in the boundary of Hn, let U be an open set of P. So since P is on the boundary, it looks like this. And here's U. Okay. Note that U set minus P is connected, or let's say simply connected. Right. Whereas if I took some point on the interior, right, then U set minus P is not simply connected. Right. And that's basically going to be the main idea, right? Is that if phi of P is not in this boundary, then you make an argument about how phi of U set minus phi of P is not simply connected. Right, because there exists a non-trivial loop which doesn't exist inside of the original, which exists inside of here. Right? And so the crux of the argument is just using the fact that this is an embedding which is open on the set U, right? And you can assume without loss of generality, you can assume U is a chart by restricting to charts. And this is one of the things on exercises to know, is that you can always restrict to a basis of charts, right? Or that for every manifold admits a basis of charts. And so you could just take a basic open set between your point and this arbitrary open set U, which is a chart, and then the map will still be an embedding with an image of the open set will still be open, because that's the definition.
Can you also do this problem with invariance of domain by including the half space into the full space, and then noting that if you are in if you're on the boundary and you get sent into the interior somehow,
Yeah.
you'll have a problem once you lift it to the full space. I might be mixing up an ordering there in order to apply this half space, or sorry, the invariance of domain argument. But like this one, looking at it, like I'm pretty sure he was like invariance of domain. But I also barely know how to use invariance of domain.
Yeah, so this seems reasonable. Okay, so like for this problem, one of the things that you get from this being an embedding is that, and in fact, you just get this from phi of U also being open in H of n, is that if U is a n ball, then its image also has to be like homotopic to an n ball or something like this. But the dimensions have to match up, that there's no way to embed H. So one thing that you get, but he just tells you this, that phi of U is also open in Hn. So I'm not like, so what you would normally use invariance of domain for in this problem is invariance of domain is exactly the thing which tells you normally that phi of U is open in the image, right? Like that's what invariance of domain gives you, right? That there's no way to that if you're embedding n-dimensional space into n-dimensional space, then the image of those open sets are open, right, in the target. So yeah, like I agree with you that invariance of domain seems to be like related to this problem, but the conclusion that I would want from invariance of domain is given in the assumptions of the problem. So I don't know if he, like, maybe he gives this problem without that assumption in like homework sets or like in his list on his website. And then for the final, he gave that assumption to make the problem easier for the final or something. But like, yeah, the thing that I would want from invariance of domain is just that yeah, because so yeah, the statement of invariance of domain is that if f from m to n is a injective continuous function, then f of u is open for all open u in m. Right? So, or rather, sorry, invariance of domain, the way that most people write it is more specific. Right? They normally write it in terms of Rn to Rm. Or maybe Rn to Rn. I don't know, the detail. I should have spent more time looking at invariance of domain. Because like I remember what the conclusion is. It's like, yeah, the image of open sets is open, but now I'm fuzzy on the assumptions of invariance of domain. Anyway, yeah, it feels like that there's a, so yeah, there feels like an invariance of domain problem hidden somewhere in this problem. I know that I have a better solution with this number 6 somewhere, so I will try to find it and post it to the website for later.
Well, I think I'm remembering slightly what I was thinking for invariance of domain, where you say, well, let's say that P is in the boundary. You can find a region around it that and suppose that it gets sent into the interior, then a region around it, around P, gets sent into the interior. And now this is a problem if you consider this as a map on the whole space, because now you've sent a closed region into the interior. Or you've sent a not open region into the interior, but now this map can be sorry, so you post compose this with the inclusion, and you see now that you've sent an open region into maybe you pre-compose, I'm not sure. You've sent a region that is decidedly not open into the I know, sorry, it's the other way around. You go from the right hand side to the left hand side. You sent something that's open to something that is, while open in HN, it's not open in the full space. And you can freely convert this into a map from a half space into the full space.
Okay.
So this at least shows you that.
Yep, that certainly works.
Yeah.
Right. So the idea is to show that phi restricted to U is, let's say, injective. then consider the restricted to U inverse, which is a map from phi of U back to U, and then use invariance of domain.
Yeah, something like that.
Yeah, so this
This
is
might not be
Raul's
exactly
idea.
what I was thinking, and I might not be correct, but yeah, like the idea was that like, well, we know we know how things behave on boundaries, right? And we know how things behave when they're away from boundaries because it's just Rn away from a boundary. And yeah, and there's only one boundary region to deal with. Like you don't have to deal with it being a weird closed set.
Well, no, yeah, like well, the invariance domain gives that U is open in Rn, but U is a half open ball, right? So you could argue that like U is not equal to like the interior of U, or U contains limit points, or just you could look at it, right?
I mean, well, it's just obviously not open.
Yes, it's obviously not open. And at this point, Wilhelm's just going to be happy that you use invariance of domain. Okay.
Right, and I think you get that phi restricted to U is injective from the fact that it's an embedding.
Yeah, and oh boy, this is a fact of an embedding that like if your differential is injective, then this means that there is a small open set such that on that small open set, your function is injective. Right, like, and it's generalizing the idea that like, just to draw a normal smooth function in R, that like, if your differential is injective, then in a small neighborhood, your original function is injective, because in small neighborhoods, the differential approximates the original function, right?
Isn't it even simpler than that? Isn't that embeddings are homeomorphisms onto their images? Or am I mixing things up?
So embeddings are homeomorphisms onto their images in the subspace topology of the image. So for example, I can embed a circle into R2, but yeah, open subsets of the circle are not open in R2, right?
Right.
So you do need to use the fact that like the image of this open set U is open in Hn, right? That's like vitally important to the problem.
Right.
But yeah. So sorry. So I guess that the thing that I was saying is slightly more general, that like if the differential of your function at a point is injective, then your function is injective at a neighborhood of that point. But embeddings have injective differentials everywhere. Right, so they are just injective everywhere. Okay. Cool. Any other problems from this final that jump out at people? If someone knows how to do 9 for the final, that would be great, because I look at that and that does not jump out at me. But I've seen 8 before. I know that I have a solution to 8 somewhere. 7 is a computation. We did 6, 4, and 5. We talked about 3 already, or we didn't talk about 3 already, but we can talk about 3. Question 2 was on the Qual in 2019, so we've all seen that from mock Qual 0. Or no. Okay. 2 is just a fact in Munkers. This is like question 2 from his final exam is just a theorem stated in Munkers. You can just read the proof in Munkers. For question 2. There's also like the exercise no document, and other things. I don't know.
Could we maybe go over number 7 to go back over like how to do that computation of the Lie bracket?
Yeah.
We only have like 10 minutes. So maybe just...
Yeah, so 7's good because it only takes 10 minutes. So I suppose that I should ask real quick, what should we all talk about? Like if I make a worksheet for Thursday, what should I make a worksheet on? Because the first 2 weeks, there were like either recommendations or it was kind of clear, right? Like I just imposed we're doing a worksheet on homology 1 week 2, right? But are there any like recommendations for like topics or problems maybe for a worksheet? So like one thing which I'm gonna propose for a worksheet is stuff on like the regular level set theorem. Because there's a class of Qual problems that use the regular level set theorem. Anything else?
I guess some Lie garbage.
By Lie garbage, do you mean like Lie bracket garbage or Lie group garbage?
Yes.
Okay. Lie stuff.
And then how likely do you think it is that he's going to torture us with mapping cone stuff? Because I do not like that at all.
So looking at past finals, he's always had a mapping code question on his final exams. He hasn't put a mapping code question on a Qual yet, but he might.
I could be wrong. I think when I was talking with him, he said he put the real version on a Qual, maybe.
Oh yeah.
Not the correct one.
Okay. So maybe we should talk about the real mapping code.
Could be wrong. The real one is a lot more recent, I think.
And we're talking about like the generalization of problem 1 of the final to the real projective space, right? It's the, yeah.
I don't know if it's a generalization, but.
Or I guess that problem 1 is the generalization of the real
yeah.
case, right? Yeah. So it's a generalization because it's the same but different. I love that phrase because it literally means nothing, right? Like, what do you mean by the same but different? Well, they're both made of matter, but that's it. That's technically the same but different. Okay. Well, if there are any other requests for a worksheet for Thursday, let me know. I'm going to try to make the worksheet by the end of the day, so that way people can maybe look at it during the day Wednesday. And also so that way I can look at it during the day Wednesday, and maybe I can appear more intelligent than I appeared today, because I will be the first one to tell you that part C is not my strongest suit, but I learned how to do most of the problems on his final exam, and then I did well in school. So that was my story of how I became successful, with super large air quotes successful at part C. Okay, so let's talk about question 7. So we want to compute a Lie bracket. Compute a Lie bracket. So we want to compute x comma y on R3 for x is equal to y dx, and I'm going to add in some extra terms just to make it like more annoying to read, but easier to point things out later. So 0 dx plus x squared dy plus y dz. And so there's a formula for the Lie bracket, which is nice, which says the Lie bracket from x to y. And this is in Lie somewhere, where it's, okay, let's see if I can remember this. It's xj, right? It's the of y? No. See, then I know that at the end it's dx j. Okay. Darn. This is my hubris. It's okay. I only have 2 bookmarks in all of Lie, and one of them is the page with this formula of the Lie bracket, because it's the thing that I always forget. So, aha. Right. So it's just x yj minus y xj. Okay. And so this is how Lie writes it in his textbook. And I suppose that I should give you the page number because I needed the page number, so you might also need the page number. So this is page 187 of Lie. For those of you who like the reference. And Lie writes it like this, but what Lie isn't writing is, because he uses Einstein notation, is that this is supposed to be like the sum from j equals 1 to 3 here, right? There's a summation that he just doesn't write because he's Lie. And when you're Lie, you get to not write sums and be like, but I meant a sum. And then everyone's just like, oh, well, I guess if you meant a sum, then that's fine. And so one thing to remember is that I could have also written this as y0, 0, and I could have written this as 0 x squared y equivalently, because tangent spaces have a basis, and these 3 differential operators are the 3 basis vectors for the basis of tangent vectors on R3. If you'd like me to talk more about that, I can, but not today. Right. And so that means that this is the first component of x, this is the second component of x, and this is the third component of x. And this is because Lie likes to use superscripts for his components, again, because he likes Einstein convention. Okay. So that means that writing this out, I have x, which is just y dx, and I'm applying this differential operator to the first component of y, which is 0. And then I have all of y, which is x squared dy minus y dz. And Actually, I'm not going to distribute that yet. I'm applying this entire differential operator to the first component of x, which is just y. And then this is all dx, right, for the first component of the basis for the tangent space. Right. Then we do the same thing. So I have x, which is still this. Then I have the second component of y, which is x squared. And then I subtract x of d dy plus y of d dz applied to 0, d dy. And then this is still x applied to the third component of y, which is y, minus this is y applied to the third component of x, which is still 0, dz. And so simplifying this out, the first thing that we'll do is we'll just like, because differential 0, 0, y times 0, 0. This is an entire big function, right? I'm taking a differential times stuff of 0. So this is all 0 and this is all 0. This is the differential of x with respect to y. So this is 0. And so this term goes to 0. Right. This second term here is the differential of z with respect to y. So that term is going to go to 0. Right. Which is wonderful. So I have a bunch of terms that are all going to go to 0. So the first thing that I get here is I get a negative x squared times the differential of y with respect to y, which is 1. So that's just x squared. And then going all the way down here, I get this times dx for the first term. And then I get 2xy dy. And that's it. Because this entire sum goes to 0. And then here, this term, I just get this times this. And here I just get this times this. So because we don't care about the order that we write these things in, might as well write it so that way the negative sign isn't floating, because people find that aesthetically pleasing. There's also a way to calculate these Lie brackets using the fact that Lie brackets are bilinear operators. So you could write out like the definitions here of y dx, and then x squared dy plus y dz, and you could be like, this is bilinear, so it's linear to the second components. This is y dx comma x squared dy plus y dx comma y dz. And then if you like use the basic properties of these Lie brackets, right, eventually you just get that this is the thing that comes out. But there is kind of a fun way of using these, the linear property of these Lie brackets, and just breaking down some of these like nice properties of the Lie brackets that they have, like these basic, like there's a, like, so like you use the fact that the differential of dxi and dxj is equal to 0 for all I and j, right? So you use these properties and you break apart these Lie brackets and you factor out stuff and eventually get this. So.
Well, so the reason we don't have the y with the negative x squared is because we took the derivative of it, right? We just got 1.
Yeah, exactly. Yeah, exactly. This was the partial with respect to y of y.
Awesome, sweet.
Can you just finish the calculation in the bilinear case? or the bilinear.
Oh, yeah. Okay. Okay. Let's see. This already makes me wonder if I've done something wrong here because
Yeah, because I can't see how you go from there to the answer.
so now I can just calculate these two Lie brackets. Well, okay, if I just want to calculate these two Lie brackets explicitly, then how come I didn't just do that beforehand? So, right, how do you pull functions out of Lie brackets? No, not that way. Where's the other form? Properties of Lie brackets, which is on right.
Or
Okay,
unless, I guess at that point, now that you have like monomials in the operators, right? You could now, like, is the first one, like you do it as y del x of x squared del y. You get a 2x coming out by taking the del x of it, but then you have a del xy showing up, which is weird.
So I guess that the thing that I'm getting to is that page 188 has like these properties, and if you use the third property here, it tells you that, hey, this first Lie bracket is going to be equal to y times x squared of the Lie bracket between dx and dy plus, then we have, which one am I saying f is? Y, then capital X is the dx of x squared. Apply this to d dy minus, like there's just a formula here that just allows you to like break up. That's just one of the properties of a Lie bracket, which breaks this into smaller Lie brackets and just evaluations of these functions. And this becomes x squared, y is d dy of y applied to d dx, and the parentheses go like this for some reason. And then, hey, you use this fact that I just said to break this Lie bracket down to 0, and then you just apply a thing for this first term. Right? So this is 2xy minus x squared, sorry, d dy, or del y. This is del x. Right? And so that means that, so that was just me breaking apart this one, which I guess I can do in red. All of this, and then if you apply the same formula, which, like I said, it's statement D on this page, right? You will necessarily get 0, because otherwise this answer up here and this answer down here are the same answer. But yeah, there's this formula which allows you to break up a Lie bracket into more basic Lie brackets. Which I guess I can just write down what the formula is. It says that fx comma gy is equal to fg, the Lie bracket of x and y, plus fx g comma y minus g y f x. So this is the formula that I applied at the red step. So And so if you don't want to do that formula because you don't like the fact that Lee doesn't use his Einstein convention or something, I don't know, for whatever reason you don't like the first method, you can use these 4 facts about the Lie bracket to continually break up the Lie bracket into less complicated Lie brackets. And in the case of like you actually computing Lie brackets, say like on the Qual or in the final or for things like this, these Lie brackets always end up being computed on vector fields on R3. And so then you can use this thing always to eventually get it down to where all the Lie brackets disappear. And that's one way to do this. Okay, I'm going to end the recording now. So goodbye to all people in the future.